welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communication systems. So far we have looked at the MMSE estimate or even the LMMSE estimate for a non-Gaussian vector parameter h bar, where h bar, and we have particularly illustrated this for a case of estimation of a multi-antenna downlink wireless channel. Okay. So now to understand it better, let us do a simple example to see how this vector channel estimate is computed. Alright. So in today's module, we will be doing an example for the multi-antenna downlink vector parameter channel estimation. Alright. So example for LMMSE. Of course, the moment I say LMMSE, you have to understand that if the parameter is Gaussian, then it becomes MMSE. Example for LMMSE estimation of multi-antenna of a multi-antenna downlink wireless channel. Okay. So we would like to do an example for this. So consider towards this example, consider a base station with m equal to 2 antennas. Okay. So we want to consider a base station with m is equal to 2 antennas. That means the base station has 2 transmit antennas, and of course the user, this as per the scenario we are considering, the user only has a single receive antenna. Later we will extend this to a scenario where the user also has multiple antennas, then it will become a MIMO channel, that is a multiple input multiple output wireless channel. Alright. So right now we are considering only multiple and transmit antennas. So it is a MISO channel, multiple input single output channel. Alright. So the system model for this can be is given as yk, which is the received symbol at time instant k, equals x1k times h1, h1 is the channel coefficient corresponding to the first transmit antenna, plus x2k times h2, plus of course vk, vk is the noise, yk is the observation, okay, and we have h1 and h2, these are the two channel coefficients. These are the two channel coefficients of the multi-antenna channel, and further what we have is that our pilot vector x of k or x bar of k, this is equal to the pilot vector x bar of k is equal to x1k x2k, where at time instant k, x1k is symbol transmitted from transmit antenna 1 and this is the pilot symbol. In fact, both are pilot symbols, this is pilot symbol from transmit antenna. This is the pilot symbol from transmit antenna 2. So we have pilot symbol from transmit antenna 1 and pilot symbol. So this is the pilot vector x bar of k, which consists of two pilot symbols, x1k from transmit antenna 1, x2k from transmit antenna 2. Alright. Now in this particular example, so each of this is a pilot vector. So this is the pilot vector at time instant k. Now let us consider 4 such pilot vectors. Consider in our example n equal to 4 consider n equal to 4 pilot vectors. Let us say the pilot vectors are x1 bar equals 5 comma 4 5 4. This is the first pilot vector. X2 bar equals 4 5. X bar 3, let us say x bar 3 equals 3 4 and x bar 4 equals 4 3. Alright, these are the 4 pilot vectors, and consider the observations, and then corresponding to this we will have, see we have n equal to 4 pilot vectors, corresponding to this we will have n equal to 4 observations. So, let the corresponding n equal to 4 observations, these be given as, let the observations be given as y1 equals 2, y2 equals 1, y3 equals 1, y4 equals 2. Alright. Let the dB noise variance be equal to 3 dB. This implies that dB noise variance means basically 10 log 10 of sigma square equals 3, which implies sigma square equals 10 to the power of 0.3, which is approximately equal to 2. We have already done this several times, that is 3 dB is approximately equal to 2, alright. So, 10 to the power of 0.3 is approximately equal to 2. So, 3 dB noise variance means noise variance is equal to 2, okay. And also we are considering IID channel coefficients. Not necessarily Gaussian, that is expected value of h bar transpose is, if you consider IID channel coefficients, and the covariance matrix will be proportional to identity. So, expected value of h bar transpose is equal to sigma h square I, where sigma h square in dB, that is 10, that is the average channel variance or the average channel gain in dB equals minus 6 dB. Now, what does this imply? This implies that sigma h square equals 10 to the power of minus 0.6, this is equal to 10 to the power of 0.3 whole raised to the, I am writing this in terms of 10 to the power of minus 0.3 because we know 10 to the power of 0.3, this is 10 to the power of 0.3 is approximately 2. So, 10 to the power of 0.3, 2 raised to the power of minus 2, this is equal to 1 over 4. So, sigma h square equals 6 dB, minus 6 dB implies sigma h square equals 1 over sigma h square equals 1 over 4. Okay. So, that is what we have. Now, what we need to do now, we need to compute the LMMSE estimate of the channel vector h bar, and of course, I have said this many times, if the channel vector h bar is a Gaussian channel vector, then the LMMSE estimate, there is a linear minimum mean squared error estimate itself is the MMSE estimate, this is the minimum mean squared error estimate. Of course, if it is non-Gaussian, then it is simply the LMMSE estimate. This is the best amongst the class of linear estimators. Alright, this is something to keep in mind. I will keep repeating this frequently because this is a subtle but very important point. Alright, so we need to compute the LMMSE estimate of channel vector h bar. By the way, this is m cross 1 channel vector, which means it is 2 cross 1, since m is equal to 2. Alright, we have 2 antennas at the base station. Now, for this, first let us form the pilot matrix X, which is equal to x bar transpose of 1, x bar transpose of 2, x bar transpose of 3, x bar transpose of 4, where x bar 1, x bar 2, x bar 3, x bar 4 are the 4 pilot vectors. So, this will simply be 5 4 4 5 3 4 4 3, and this is a pilot matrix. This is a pilot matrix, which is, remember, n cross m, that is n is equal to 4 and m is equal to 2. This is an n cross m pilot matrix. Okay. So, now, so we have the pilot matrix. Remember, this is your X, which is the pilot matrix. This is the first important aspect of multi-antenna channel estimation. We have to form the pilot matrix. Next, we form the observation vector, that is y bar. Remember, y bar is n cross 1, where n is the number of observations. Okay. Next, we form the observation vector y bar equals y1 y2 y3 comma y4, which is basically your 2 1 1 2. And now recall, so this is your observation vector. Okay. So, observation vector is y bar, and y bar is n cross 1, this is equal to 4 cross 1 observation vector. Now, recall the MMSE estimate, recall the LMMSE estimate, or MMSE recall the, to be more precise, the LMMSE estimate, linear minimum mean squared error. Recall that this is given as h hat, which is the LMMSE estimate, equals, we derived this in the previous module, sigma h square x transpose x plus sigma square identity inverse times sigma h square times x transpose y. Okay. Now, remember, again, once again we pointed out in the previous module that this is a much more simpler version, that is computing x transpose, that is sigma h square x transpose x plus sigma square identity inverse, because look at this, x is 4 cross 2, therefore x transpose x will be 2 cross 2, this is a 2 cross 2 matrix. Okay. So, inversion of this 2 cross 2 matrix is much more simpler, but if you were considering x transpose, that is the other version, other formulation based on x transpose, then that will be a 4 cross 4 matrix. So, we have to compute the inverse of 4 cross 4 matrix, which is much more complicated compared to this, which is much more simple. Okay. So, now I will proceed basically. Now, of course, one can also now notice that I can also simplify this slightly by bringing out the sigma h square sigma square. I can write this also as, first let us bring out sigma h square. So, x transpose x plus sigma square by sigma h square inverse. Of course, when sigma h square comes out, it comes in the denominator, that cancels with sigma h square. So, this becomes x transpose y bar, and now bring out sigma square. So, this becomes x transpose x by sigma square plus 1 over sigma h square times identity. Of course, here there is an identity missing, sigma h square times identity into inverse into x transpose by sigma square times y bar. It is slightly more convenient to use this formulation. Now, let us compute this matrix. So, let us compute this matrix x transpose x divided by sigma square plus 1 over sigma h square I inverse. So, now towards this, first let us start by computing x transpose x. We know x, that is a pilot matrix. So, x transpose x, simply take the transpose of x. So, this is 5 4 4 5 3 4 4 3 5 4 4 5 3 4 4 3, transpose of the matrix into itself. You can compute this, correct. This is your x transpose, this is your x, okay, and this will become, this is basically your 66. You can compute this thing is 66, 64, 64, 66 is a symmetric matrix. Of course, since x transpose x is symmetric matrix, the transpose of this matrix is equal to itself, and naturally you can see that this is a symmetric matrix, a symmetric 2 cross 2 matrix. Okay. Now, let us compute this quantity 1 over sigma square x transpose x plus 1 over sigma h square identity. This becomes half 66 64 into 64 66 plus 1 over sigma h square. Sigma h square is 1 by 4. So, 1 over 1 by 4 times identity 1 0 0 1. Of course, this is the 2 cross 2 identity matrix, that is the m cross m identity matrix, which will be equal to, now you can compute this thing, this will be 33 32 32 33 half of x transpose x plus 1 over 1 by 4 times identity matrix is 4 0 0 4. This will be equal to 37 32 32 37. Okay. And now you can see we can compute the inverse of this matrix easily. The inverse of this matrix is 1 over the determinant, since this is a 2 cross 2 matrix, that is 1 over 37 square minus 32 square, that is 37 square minus 32 square times, switch the diagonal elements 37 37 because both are same, negative of the of diagonal elements minus 32 comma minus 32, and this will becomes 1 over 37 minus 32 square is 37 minus 32, that is 5 times 37 plus 32, that is 69 times, of course, 37 minus 32 minus 32 37. Okay. Yeah. Now, let us compute this other quantity 1 over sigma square x transpose y. Further, 1 over sigma square x transpose y bar is, what is this? This is 1 over sigma square times x transpose y bar. So, sigma square is 2. So, 1 over 2, x transpose is 5 4 4 5 3 4 4 3 times 2 1 1 2, which is equal to half 25, 23. And now therefore, so we have computed both these components 1 over sigma square x transpose y and the other, alright. So, now we put these both these things together to compute the final LMMSE estimate. Therefore, the LMMSE estimate is given as therefore, the LMMSE estimate, this is given as h hat is equal to, the first part is 1 over sigma square x transpose x plus 1 over sigma h square identity inverse into 1 over sigma square x transpose y bar. We have computed both these quantities above. This will be basically your 1 over 5 times 69 into 37 minus 32 comma 37 times this quantity, that is 1 over sigma square x transpose y, that is half, we have over here 25, 23, that is a column vector 25. It should be clear to you that this is basically 1 over sigma square x transpose y, and this quantity is basically this 1 over sigma square x transpose x plus 1 over sigma h square I inverse. Okay. And now you multiply these two things together, and what you are going to get is basically 1 over 690 times, and you can check this 125 plus 64, 115 minus 64 equals 1 over 690 times, well, this becomes 189 comma 115 minus 64, that is 51. So, your h hat is basically, if you write it explicitly, 189 divided by 690, and the second component is 51 divided by 690, and taking 3 common both the numerator and denominator of each component, what we have is 63 divided by 230 and 17 over 230, and therefore, what we have is net LMMSE estimate h hat equals, let us just write this down, 63 divided by 230, 17 divided by 230, and it is slightly complicated to compute, more complicated to compute than the simple least squares estimate. People will realize because of the complicated nature of the expression for the LMMSE estimate. So, this is basically your LMMSE estimate of your channel LMMSE estimate of the channel vector h bar. And therefore, now if you look at this, h hat basically is the estimate of the channel vector h bar itself is a channel vector corresponding to 2 transmit antennas, therefore, it has 2 components, alright. So, h hat is basically of the form h1 hat which is estimate of channel coefficient 1 and h2 hat which is estimate of channel coefficient 2. So, this is 63 by 230 and 17 by 230, which implies that basically now if you just write it explicitly again, although it's all of these are very clear from the example, just to write this a little bit more explicitly, this 63 by 230 and H2 hat equals 17 by 230. What is H1 hat? Estimate of H1, that is channel coefficient 1, estimate of channel coefficient H1, and what is H2 hat? This is your estimate of channel coefficient H2. This is the estimate of channel coefficient H2. Alright. So, this completes our example for the LMMSE estimate of the vector parameter, which is the multi-antenna channel vector for the downlink. Okay. So, what we have done in this is we have considered a simple example for multi-antenna downlink channel estimation with m equal to 2 antennas, n equal to 4 pilot vectors, considered the pilot matrix, the observation vector, illustrated how to compute the LMMSE estimate. Alright. We have derived the LMMSE estimate from which one of the channel vector, from which one can extract naturally the LMMSE estimates of the individual channel coefficients. Alright. So, we will stop with this and continue with other aspects in the subsequent modules.